And I wanted to revisit that Fermat's theorem and say a few words about that and maybe write down a quick proof using a limit argument. So here's what Fermat's theorem says. This is the thing that allows us to throw out all but finitely many points when we're checking for extreme points, right? So if f has a local max at x equals c, then f must have a critical point at x equals c. So another way to think about that, if you remember your logic, is that if f does not have a critical point, then it cannot have a local max or a local min. So this is really just a test, right? So we can throw out a bunch of things that aren't the critical points and just check the critical points. But critical points may or may not give local extreme points, right? So the reverse arrow is not true. So here's what the logic arrow looks like, right? If the thing has a local max or a local min, then it must be a critical point there. The reverse arrow is not true. Just because you might be a critical point does not mean that you attain a max, a local max, or a local min. And here are two examples, right? If f of x is equal to x cubed, then f prime is 3x squared. And so we know that f prime of 0 is 0, right? So that means x equals 0 is a critical point of the function x cubed. But here's what x cubed looks like. Here's the critical point 0, but that thing is not a relative max, nor is it a relative min, right? As you can easily see, right, there's no open interval about 0 such that f of 0 is the highest point or the lowest point. In fact, it'll always be stuck somewhere in the middle, right, no matter what open interval you draw. And so another example, right, just because your derivative does not exist there doesn't mean that you have a max or a min. So let's take x cubed and look at its inverse. So basically take this thing and turn it on its side. So what's going to happen there? Well, the inverse function of x cubed is the cube root of x. And so let's see what happens there, right? So f of x is x to the 1/3. F prime of x is 1/3 cube root of x squared. And so f prime of 0 does not exist. That means x equals 0 is a critical point of the function, the cube root of x. But when you look at a graph, right, it's just this thing turned over on its side. So what happens at 0? Not a max or a min, but there's a vertical tangent, right? There's a vertical tangent, so there can't be a max or a min. So again, be very careful. The reverse arrow does not hold in this Fermat's theorem. All right, let's look at a quick proof of why Fermat's theorem holds. So we want to show that if there's a local max or a local minimum, then we have a critical point. So I'm going to do the case where we've got a local maximum, and I'll show that that must force a critical point. So if we have a local maximum, then either the derivative is 0 or the derivative does not exist at that local maximum. So suppose f of c is a local maximum, right? What does that mean? Well, we'll say what it means in a second. If the derivative at c does not exist, then we're done. That means there's a critical point at x equals c. So either the derivative does exist at c or it doesn't exist at c. So two options. We've just dealt with one of them, right? If the derivative does not exist, we are done. So now if the derivative does exist, we need to show that that derivative is equal to 0. Okay. So suppose f prime of c does exist. We know that f of c is a local maximum. What does that mean? That means in some open interval, right, containing c. So some open interval containing c, I know that f of c, right, so here's f of c. I know that that's going to be the highest point out of all the numbers in the open interval from a to b. So, right, f of c is the highest point for all x's among all those x's that are close to c. So let me look at c plus h, where h is small, right? H is something near 0. right? So I can take h small enough to where it lives in this interval from a to b. Now, what happens if h is positive? Well, if you look at f of c plus h minus f of c, what's that going to be? Well, we've got a small thing minus a larger thing, and so this numerator is going to be negative, right? The numerator is going to be negative, and if h is positive, then that means the denominator is going to be positive. So what does that say about this fraction? We've got a negative over a positive. That means this fraction is negative. So now when I take the limit of both sides, right, if a function is always below the x-axis, then when I take a limit as x approaches some number, that limit will have to be below, right, at or below the x-axis. So the limit as h approaches 0 from the right of this fraction must be less than or equal to 0, right? The fraction is less than 0, therefore the limit must be less than or equal to 0. But I know the limit as h approaches 0 exists because f prime of c exists, right? So, right, whenever the limit exists, the left-hand limit is equal to the right-hand limit, and they must be the same. So the limit as h approaches 0 from the right is the same thing as the limit as h approaches 0, right? So that means this limit now must be less than or equal to 0. This is exactly f prime of c. That means that f prime of c must be less than or equal to 0. So now you want to check the same argument. I didn't write that all down, but we can just point to it. Now we want to check what happens when h is less than 0, right? So again, the numerator is still negative, right? It's a smaller number minus a larger number, right? Smaller number minus a larger number. And so the numerator is negative. And now if h is less than 0, then h, the denominator, is negative. So there we would have a negative over a negative. Now this thing becomes a positive. And so the limit as h approaches 0 from the left is now positive. Well, again, it's differentiable, so the limit as h approaches 0 exists. Therefore, the limit as h approaches 0 from the left is equal to the limit as h approaches 0 from the right. Right, they're all the same. So instead of writing limit as h approaches 0 from the left now, I can just write limit as h approaches 0. And again, all of these things are now becoming positive, right? Because this fraction is positive. So if h is less than 0 now, this is positive, therefore this thing is positive, therefore this thing is positive. And so now that tells us that f prime of c must be positive, or I guess non-negative is a better word. And so now we've checked that f prime of c is bigger than or equal to 0, and we've shown that f prime of c is less than or equal to 0. The only way both of those things can happen is if f prime of c is equal to 0. You should, as an exercise, write a proof that if f of c is a local minimum, then f prime of c must be equal to 0. That would be a good exam question.